Some locomotives were so dangerous they killed their own crews. From boilers that exploded like bombs to cabs that cooked men alive, the history of rail is written in steam and blood. In this video, we will discover the 10 deadliest locomotives ever built, machines that railroad companies desperately want you to forget. Number 10. Camelback Locomotives. Starting in 1877, American railroads began building locomotives that looked wrong from the moment you saw them. The engineer's cab sat perched right on top of the boiler, straddling the machine like someone riding a mechanical bull. This was not some designer's fever dream. It was the railroad industry's solution to burning anthracite coal waste, a cheap fuel found throughout the northeastern United States. The problem was the Wooten firebox. To burn that stubborn coal efficiently, they made the firebox so massive it could not fit between the wheels in the usual spot at the rear. So designers did the only logical thing. They mounted the engineer's cab halfway down the boiler and left the firemen alone on a tiny exposed platform at the back. Think about that. The engineer sat just inches above a roaring firebox, completely cut off from his firemen by tons of steel and deafening noise. Communication was reduced to shouting or banging on the boiler with a wrench. Heat radiated through the floor constantly. Visibility forward was compromised by the boiler's bulk, and if anything went wrong, the engineer was sitting directly on top of the explosion. Injury records from the era tell the grim story. Camelback crews suffered twice the accident rate of standard engine crews. Burns, hearing damage, and fatalities were disturbingly common. The Interstate Commerce Commission finally banned new Camelback construction in 1927, citing unacceptable risk to operating personnel. These locomotives proved that chasing fuel savings could twist a machine's shape and put the real cost squarely on the men who ran them. Between 1914 and 1916, Alco built something for the Erie Railroad that was not just big. It was a mechanical dare that pushed the limits of steam power into the realm of the absurd. This 28882 behemoth had 3 sets of driving wheels, including one set tucked under the tender. That meant 24 powered wheels clawing at the rails, all fed by a single boiler. On paper, it could generate tractive effort of 160,000 pounds, enough to snap couplers and rip yard tracks apart. Crews quickly found out that was the easy part. The real nightmare began when the Triplex tried to move at anything faster than a crawl. The boiler simply could not keep up. It would starve the third engine set of steam, causing pressure to collapse above 15 miles per hour. Test data from the Erie Railroad's own record show performance dropping off a cliff once the train left the yard, with the massive cylinders gasping for steam before the train even hit mainline speeds. But here is where it gets dangerous. When steam pressure dropped suddenly, the locomotive became unpredictable. Crews reported the engine lurching and stalling at the worst possible moments. The valve gear adjustments were constant battles. Boiler tube leaks threatened scalding eruptions. Downtime far outpaced actual running hours. Yard workers nicknamed it the Yard Ripper because while it could drag a mountain of coal cars out of the terminal, it could barely make it to the next town without something going catastrophically wrong. The Triplex stands as a cautionary tale. Sometimes adding more power just means finding new ways to create disaster. In 1929, the locomotive rolled out of the shops looking more like a submarine than a steam engine. Under its smooth, streamlined shell, it hid the boldest and most dangerous experiment in the British railway history. It used a water tube boiler borrowed from warship technology, operating at pressures that made experienced engineers nervous. Instead of a simple fire tube design, the engine used a maze of narrow pipes to withstand pressures up to 450 pounds per square inch. That was roughly 3 times the pressure of conventional locomotives. Higher pressures meant more steam from less coal. On paper, it was the future of railway efficiency. In reality, it was a ticking bomb. The W1 had secrets that ran deep. Test runs were shrouded in mystery, with engineers sworn to silence and the press kept at bay. Diaries from the National Railway Museum tell of endless hours spent coaxing the boiler to behave, fighting scaling and foaming that clogged the delicate tubes and threatened sudden, catastrophic failure. A single missed deposit in those narrow passages could trigger a cascade of leaks. And at 450 pounds per square inch, a leak was not a maintenance issue. It was a potential death sentence. Maintenance crews dreaded every inspection. The boiler ran hot, demanded constant attention, and the locomotive spent more time in the shops than on the main line. Only one W1 was ever built, and that was probably for the best. The W1, nicknamed Hush Hush, was a beautiful phantom, haunted by the gap between radical ambition and the stubborn, dangerous reality of extreme pressure steam. Number 7. Bulleid Leader Class. In 1949, post-war Britain was desperate to modernize, and steam had to fight for its place on the rails. Enter the Bulleid Leader, a locomotive that looked like a diesel and tried to act like one too. Oliver Bulleid's vision was radical. A fully enclosed, double-ended machine, oil-fired and equipped with a mechanical stoker. The wheels and drive gear were boxed inside a metal shell, hidden from view, and supposedly shielded from the weather. In theory, this meant cleaner lines, less crew exposure, and easier operation. Just drive from either end. No need to turn the engine, but the reality inside the leader was far from comfortable. It was hell. Heat built up in the sealed body, filling the cab with stifling air and engine fumes. Temperatures regularly exceeded 120 degrees Fahrenheit. Crews sweated through shifts with poor visibility and almost no fresh air, breathing in exhaust that had nowhere to escape. Maintenance teams found themselves crawling through tight, greasy corridors to reach the wheel sets, cursing the very enclosure that was supposed to keep things modern. Union minutes from 1950 are filled with complaints about the working conditions and the near impossibility of keeping the machinery clean or cool. The leader ran a handful of test trains, but by 1951, the experiment was over. Every unit was scrapped, the bold dream buried under a mountain of maintenance logs and union grievances. The leader proved that you could disguise a steam locomotive in a diesel clothing, but you could not make it livable for the men inside. In 1944, Baldwin built something that looked like it came from science fiction. A 123-foot-long machine sheathed in streamlined steel, driven not by pistons but by a direct-drive steam turbine. The S2 was a bold attempt to bring jet-age technology to the rails, promising 6,900 horsepower and a ride smoother than any conventional steam engine. But the heart of the S2 was its gamble, and that gamble nearly killed people. Turbines thrive on steady, high-speed running. On the open main line above 40 miles per hour, dynamometer logs from Altoona show the S2 approaching diesel-like efficiency, its turbines spinning at full song. But the reality of freight railroading is far from constant. Trains crawl out of yards, stop for signals, and grind up grades. At low speeds, the S2's turbine became a liability and a danger. Test data from the Pennsylvania Railroad's own records reveal a harsh truth. At 20 miles per hour, the S2 devoured coal and water 2 to 3 times faster than a standard 284. The boiler struggled to keep up with steam demand, often leading to pressure drops and sluggish starts. Engineers noted the difference instantly. The S2 was eerily quiet at speed, but at a crawl, it was all steam and no go. When the boiler could not keep pace, the turbine would hunt and surge unpredictably. Crews reported near-miss incidents where the locomotive's behavior became erratic under load. The S2 ran for just a few years before being sidelined, not for lack of vision, but because the railroad needed a locomotive that would not surprise its crew at the worst possible moment. In 1947, this locomotive looked like a vision of the future. A long, low shell wrapped in smooth steel gliding across the rails with barely a sound. Under that streamlined body, though, was a machine locked in a battle with itself. And that battle created some of the most dangerous operating conditions any crew ever faced. The M1 was a steam turbine electric locomotive. A coal-fired boiler made steam which spun 2 turbines that powered electric generators. Those generators fed traction motors on every axle. On paper, this promised the best of both worlds, the smooth pull of electric drive and the raw force of steam. Every mile revealed a new weakness and a new hazard. Coal dust and ash, the constant companions of steam, found their way into the turbines. They coated blades, clogged passages, and ground down delicate parts. Maintenance logs from the late 1940s read like a litany of frustration. Turbines fouled, generators running hot, traction motors tripping out under heavy load, but the real danger was the heat. The M1's heat was relentless. Crew reports tell of electrical cabinets hot enough to scorch a hand on contact. Cooling fans never seemed strong enough to keep up. Even the streamlined casing became a liability, trapping smoke and heat inside and turning the engine room into a furnace. Men working in that space risked burns, heat exhaustion, and worse. The M1 ran for less than 5 years before the railroad gave up, sidelining the experiment as a beautiful, expensive warning. It stands as proof that even the most ambitious hybrid can be brought down by the simplest enemies. Heat, dust, and the stubborn realities of coal-fired steam do not care how futuristic your locomotive looks. Number 4. South African Class 25 condensing. In 1953, South African railways faced a problem as old as the desert itself: water. The answer arrived in the form of the Class 25 condensing, a 484 machine that turned its own exhaust into a lifeline. Instead of wasting steam in thick clouds, these locomotives captured it, funneled it through a maze of radiator tubes, and cooled it back into water, ready to be used again. The result was a tender so massive and packed with machinery that it dwarfed the locomotive pulling it. With 6 steam-driven fans and more than 2 miles of radiator piping, the tender looked less like a train car and more like a rolling factory. On a good day, the system could recover up to 90% of the water, stretching the range to nearly 500 miles between stops. But all that complexity came at a terrible price. Radiator tubes clogged with scale constantly. The fans demanded attention that distracted crews from other duties. The sheer weight of the tender wore down the rails and stressed every component. But the real danger was in the maintenance. Workers had to navigate miles of superheated piping where a single leak could mean third-degree burns or worse. Maintenance logs from the 1960s tell the story of crews battling fouled pipes and failing pumps, sometimes spending more time cleaning than running, always at risk. The Class 25. Condensing was brilliant in theory and spectacular in person, but its thirst for dangerous upkeep eventually outpaced even its ability to save water. Some problems cannot be engineered away. They can only be endured. In the 1830s, nobody really knew how to build a safe locomotive. The Grasshopper engines, named for their distinctive vertical boilers and walking beam drive mechanisms, were experiments in motion. They were also experiments in how many ways a steam engine could kill its crew. These early machines featured vertical boilers that looked like industrial chimneys on wheels. The design was compact, but it concentrated enormous pressure in a small upright vessel with primitive metallurgy and even more primitive safety valves. Boiler explosions were not rare events. They were expected hazards of the profession. When a Grasshopper boiler let go, it did not just fail, it detonated. The vertical design meant the explosion went straight up and outward, showering the crew and anyone nearby with scalding water, superheated steam, and jagged metal. Contemporary accounts describe scenes of horror. Engineers and firemen were killed instantly, bystanders were maimed, and wooden station buildings were set ablaze by scattered coals. The safety technology simply did not exist yet. Pressure gauges were unreliable. Safety valves stuck closed. Boiler plates were inconsistent in quality, with hidden flaws waiting to become catastrophic failures. Crews operated these machines knowing that any trip might be their last. The walking beam mechanism added another hazard, with exposed connecting rods that could snap and sweep across the platform. The Grasshoppers served their purpose in proving that railroads could work in America, but they wrote that proof in blood. The lessons learned from their failures eventually led to better boiler designs, proper inspection regimes, and safety standards that saved countless lives. But those lessons came at a terrible cost, paid by the pioneers who ran these primitive, deadly machines. The Beyer-Garratt looks like a locomotive that couldn't make up its mind. 2 engines at either end with the boiler and cab suspended in the middle, floating above the rails. At first glance, it seems bizarre. This 3-part design wasn't just for show. On the narrow, lightly built tracks of Africa and Australia, traditional steam engines sank bridges and buckled rails. The Garratt solved that by spreading its weight across 2 powered bogies. In East Africa, the massive 59-class Garratts hauled trains over 2,000 tons across bridges that once struggled with half that weight. Crews described them as the engine that bends twice, able to snake through tight curves and keep going where rigid locomotives would stall. But that flexibility came with dangers that rigid locomotives never faced. The articulated design meant flexible steam joints connecting the boiler to the engine units at each end. These joints were under constant stress, bending and twisting with every curve. They needed constant attention, and when they failed catastrophically. Superheated steam at several hundred degrees would erupt from the broken joint directly into spaces where crew members worked. The Garratt's odd shape and shifting weight made it a handful on a rough track. The center-mounted cab rode above the pivot points, subjecting crews to violent motion on uneven rails. Derailments were not uncommon, and when a Garratt went off the rails, recovery was a nightmare. Some Garratts served for decades, but they demanded respect and attention that lesser locomotives never required. The design that made them capable of impossible routes also made them unforgiving of any lapse in maintenance. Many crews learned that lesson the hard way. Number 1. Norfolk and Western John Henry. In 1954, the last gasp of steam power came in the form of a machine that looked nothing like its ancestors. Norfolk and Western's John Henry stretched nearly 161 feet from end to end, wrapped in a boxy shell that had more in common with a diesel-electric than any classic steam engine. Underneath that hulking body, though, was a gamble no other railroad dared. A coal-fired steam generator fed a direct drive turbine, which in turn powered electric traction motors on every axle. The idea was simple on paper. Take the smooth, powerful pull of a turbine, the flexibility of electric drive, and the raw energy of coal. Combine them into a single, unstoppable locomotive. In practice, John Henry became a rolling laboratory for every way steam technology could go wrong and hurt the people operating it. Coal, dust, and ash, the constant byproducts of its own boiler, crept into turbine blades and generator windings, grinding down delicate parts and choking the machinery. Maintenance diaries from Roanoke shops are filled with notes about clogged filters, burnt-out motors, and turbine failures that left the engine stranded miles from help. The controls were a maze of switches and gauges, more airplane cockpit than locomotive cab. Even the most experienced crews struggled to keep the systems balanced. The heat inside the John Henry's engine compartment was brutal, worse even than the M1. Electrical fires were a constant threat. The complexity meant that any failure cascaded into others, and crews never knew which system would give out next. Every trip was a test run, every mile a risk. Despite its size and promise, John Henry spent more time in the shop than on the rails. In less than 3 years, it was retired, beaten not by competition, but by its own complexity. Press releases from 1958 read like a quiet obituary for an era. The age of coal-fired innovation had ended, replaced by the steady hum of diesel-electric engines. John Henry was more than just an experiment. It was the final, towering statement of faith in steam, a machine that tried to turn an entire train into a moving power plant. When it failed, it did not just close the book on bizarre steam locomotives. It drew the curtain on a century of coal, fire, ambition, and the men who paid the price for progress. No locomotive ever tried so hard to keep steam alive. None made its end so clear. And that's all, folks. These were the 10 deadliest locomotives ever to terrorize the world's railways. Don't forget to subscribe so you don't miss future updates. Here's another video I have specially selected for you. See you next time.